Good morning, hello, good day. It's a continuation of our ESSI lecture series. Today is July 7th. It's around 11 in the morning. All three of us are in California. Today, Mr. Wang is going to talk about input of seismic waves, plane waves at any angle with any signal into finite element models. And this is based on some solutions from 1950s. Very powerful method because you can stress test your system and so on, and we'll make comments as we go along. So today again with me are Dr. Han Yang.
Good morning, everybody. Hello.
And Mr. Heshan Wang, who's going to talk today.
Hello, hi, everybody.
Good. So let me see. I need to allow you to share your screen, I think.
Okay.
Okay. So go ahead. Try to share your screen, and then we'll go along, and then we'll make comments as we go along. Try to share your screen, please.
Okay. So now can you see my screen?
Yes.
Okay.
Just share your screen, and then one other thing. I think try to make it. Let's see.
Make it like one page.
Well, yeah, one page. That's right. But for some reason,
okay,
I don't see the side. Why don't I see the side? Heshan, can you try? Since you're sharing your screen, can you try? View options. Oh, okay. No, I can see it now. But because I'm recording, I guess I have to. How do I show things on the side? I'm not sure. Well, anyway, I think they actually record on the side. So there are pictures of us and a few on the side. Okay, well, go ahead, please. Yes.
So today we're going to continue to talk about how do we develop the DRM motions from the inclined three component, which we call the 3C seismic motions. And so in our previous lectures, we already talked about how do we generate the DRM motions from 1C, which is one component, or 3 times 1C, which is the 3 times one component. Essentially, you have one component motion, the 3 different directions, and from seismic records to generate the DRM motion from that. And today, so we're going to talk about the 3 component. So in reality, so most of the earthquakes, the motions generated by earthquakes are actually 3 component, especially very inclined seismic waves. They might have some incident inclined body waves, P wave or S wave, or they might have some surface wave, which is a Rayleigh wave or lava waves. And so here we are preparing a video to show that how much the difference can be, when you have a structure that are excited by 3C realistic seismic waves and corresponding simplified 3 times 1C seismic waves. So let me show you the video. Let me see. Can you see the video?
Yes, it is running. So note. So the left video is a realistic 3-component wave field, an inclined wave that goes inside and excites all these surface waves and so on. And then on the right side is 3 times 1C wave, which is essentially taking the surface wave. I mean, taking measurements of the surface and pretending that they're 1D wave this, 1 component wave this way, 1 component wave this way, and so on. So
yes, that's true. Yeah.
So a clear difference of response.
Yeah. So even so, when you compare this to wave field, if we compare only the central point, this 3 times 1C can capture the response of that central point, but essentially it missing all the special invariant feature, and also you can see in this 3C wave field there are some like a surface rolling pattern of the motions. And these motions might have some, additional rocking response, cause this rocking response to the structure. So the response can be quite different if you neglect this very important wave feature.
Clearly, very different response. So one has to be careful by using these so-called 3 times 1D or 3 times 1C waves, because they're not. I mean, they do replicate one point, but the actual response is totally different. Anyway, go ahead, please.
Yeah. So we will go back to the slides. Okay. Okay. So yeah. So specifically today we're going to talk about 3C seismic motion is generated from incident inclined plane seismic waves. So this is an illustration of the wave field. So we might have a layering ground, and we will have some incident P wave or incident SV wave from the bottom, and then these incident waves will creating both have some reflection or refraction through the different layers, and they will have for each layer they will have some incident P wave or SV wave, and they also have some reflected or refracted from other layers, the S wave and the P wave. So for such a yeah, yes, professor, yeah.
I mean, we actually covered, you covered this, we covered this in one of the lectures before, right? We went through this.
Yeah,
I think
yes,
so.
I think, yeah.
Yeah, good.
So yeah, we have, yeah, as professor said, we can solve such a layering system through the wave potential formulation, and we can solve such a system using Thomson-Haskell propagator matrix technique. So if you want to know more about the theoretical details, you can look at this reference or go to our previous lectures. Yes. And then today our goal is to develop such a 3C free field seismic motion for the DRM input from the inclined incident plane seismic waves. And in order to do that, you're going to need three components of information. Number one, you're going to need the information about your DRM layer. Essentially, you need to specify the geometry and the location of your DRM, and what are the boundary nodes and the exterior nodes of your DRM layer. And number two, which is also very important, is you need to specify your engineering site characteristics. And in addition to that, you also need some information about your inclined incident seismic waves. So in Real-ESSI, we provide two ways for you to specify such information. You can either specify the wave potential magnitude of the incident P or SV wave. You can also specify the whole time series signal of the incident waves. So we're going to first talk about the information of your DRM input. So again, we're going to specify such a DRM information using a single HDF5 format. And actually this file should be the same, should keep the same format as we used yesterday, as we used in when you develop the 3x1C DRM motions. So actually we talked the format very detailedly, the format of this HDF5 in our previous lectures. So essentially it should have you should have these six different data sets in your DRM input HDF5. And for the format or the content of this data set, you can go to our previous lectures to see what this information and how the format is organized. Yeah, essentially it's the same. Yeah.
Yeah, and in lecture notes there's a detailed description of this format and how is the HDF5 database organized. Yes.
Yeah, and yeah, for your if you want to generate such a file, such HDF5, you can either using our preprocessor called GM-EASY to automatically generate such a file according to this format. You can also generate this file using any like general programming language like Python or MATLAB. Yeah, if you have all this information. And so then we're going to talk about how do we specify the engineering side characteristics. For the 3C seismic motion, the engineering side characteristic information is a little bit different. So remember that when you do the 3x1C seismic motion seismic motion analysis, you only need to specify a single wave velocity, because essentially it's a 1D motion. You can either specify the shear wave velocity for the horizontal direction or the P wave velocity for the vertical direction. But now when you want to do a 3C seismic motion analysis, you need to specify both shear wave velocity and the P wave velocity. So essentially now you have a 5 column in your simple in your plain text file. The first column going to be your shear wave velocity, and the second column going to be your P wave velocity. And also you also need to have density for different layer, and have a damping ratio for different layer, and also the thickness. And again, this file, the numbers does not have any units, but you need to specify the units of corresponding to these values in the DSL of the Real-ESSI.
Yeah, so
And
in the input file, you have to specify what are units here for these, because we are very keen on specifying units. Yes.
Yes, yeah, that's true. Yeah. Again, we have a big important note here. This ground profile is very important, and it should be kept the same as the profile of your DRM layer and your inner soil layer when you use the in your FEM model for wave propagation. So
So,
if you, yeah,
so,
yes,
so again, a note. I mean, there are some problems with some users actually making a slight mistake, specifying one type of profile here, and then using a different profile in the finite element model, and that created problems because you get a different wave field, and then DRM goes crazy. So you have to make sure that your profile that you specify here is the same as the profile in your finite element model. So all the layers that you specify here have to be present in the finite element model with appropriate material properties and so on. This is really important. I mean,
yes,
this is just to be consistent. You have to be consistent with your profiles. The profile that you use to create your wave field has to be the same as the profile you use to propagate waves in the finite element model. Very
yes,
important
that's
note.
true.
Yes, thank you for putting this in
Yeah,
big red.
yeah. Yeah. So then once you define your DRM information, you define your engineering side characteristics. Now you can move forward to define your information about your incident inclined plane P or SV wave field. As I mentioned before, you can define either by specifying the wave potential magnitude or by specifying the whole time series signal. And once you define such a wave field, we have another DSL command that enabled you to generate the DRM input motion from the defined plane wave field. So let's first talk about how do we define the inclined plane wave field through the wave potential magnitude. So when you define the plane wave field using wave potential magnitude, you need to realize that actually you are specify your input a harmonic excitation, and the magnitude of this harmonic excitation is related to your potential magnitude that you are specifying through this formula. And here the omega is the angular frequency of this harmonic excitation. And the V is the wave velocity of the incident wave layer. And one important note is that the unit for the wave potential magnitude should be meter square. So yeah, and this is the DSL in Real-ESSI that we provide for you to specify such a wave field. And we're going to show an example here. For example, here I'm defining the wave field, inclined plane wave field number 1 by specifying the anti-clockwise angle of the SV wave plane from x-axis is equal to 30 degrees. So this is the command, the parameter that you specify the plane where you are propagating your the SV wave. So essentially, this wave propagation plane have a 30-degree angle anti-clockwise from the positive direction of the x-axis. Yes, Professor.
So,
Yeah.
so again, I always had questions about this. So essentially what you have is a right-hand coordinate system, X, Y, Z. Z is the
Yes.
vertical axis. And you're now trying to place a plane of propagation, the plane of polarization for SV wave. And here
Yes.
you specify it to be 30 degrees off from X anti-clockwise.
Yes.
And then of course, then you will actually also specify the angle, how steep the actual wave is. But yes, so this is important. This is in space, you have to specify where this plane is, where
Yes.
the wave propagates according to your global coordinate system XYZ. Yes, go ahead.
Yes, yeah, that's true. Yeah. And then the second one, you need to specify your wave potential magnitude. So here we have specified the magnitude as 10 meter square. And then the third, as the professor mentioned, that you need to specify the angle of your incidency. So here we have specified a 60-degree angles. So this angle is the angle between the direction of your wave propagation direction and also the V axis, the vertical axis. So
Yes.
here it has been 60 degrees. And also the frequency of this harmonic excitation is about 5 hertz. And we specify the time step of the motion is 0.005 seconds. And also we're modeling the duration of the wave to be 1001 time steps. So here you specify the profile of the engineering site to be the plain text that you already prepared according to that 5-column format, and then you have a bunch of units here, which corresponding to the values of that plain text file. And from that equation, we can calculate that actually the harmonic SV wave magnitude displacement magnitude we are specifying is around like 0.3 meters. And we found that this harmonic excitation can be quite useful for some, stress test of your to generate some stress test motions of single harmonic frequency and inclinations. You can change this frequency and inclinations to do a bunch of stress tests of your engineering objects to find which is the critical situation of the seismic loading. Yes. And other than that, you can also define the whole time series signal of your incident plane P or SV wave. Again, we're going to follow, you can write the time series signal into the plain text file, and it should follow the two-column format. The first column is the time, and the second column is the corresponding acceleration or displacement ordinate. And again, very important note here is that you should make sure the signal that you are input to the system should be already being baseline corrected. Because in the later on, we're going to enable you to add some compensation time. And if you do not baseline correct your motion, when you're padding zeros to these signals, it will generate some high frequency components. So it's very important to make sure you baseline correct all your input seismic signal.
Yes.
And this is the DSL of that where you can specify the input time series signal. Essentially now, instead of specify a single wave potential magnitude, now you specify the file for the acceleration file and the acceleration unit, the file name of the displacement signal file and the corresponding displacement unit. So this is the example. So here we have specified the Kobe acceleration record that we have defined in the previous plain text file, and also corresponding displacement information. Also, all the other parameters should keep the same. And now, if you specify the signal, you can have an additional parameter, which is the compensation time that we already discussed in our previous lectures. Essentially, it will put in some zeros into the original input signal that you are provided. And once you define such a wave field, either through wave potential magnitude or either through specifying the whole time series signal, you can then generate your DRM motion through the defined wave field. So this is very simple. So just a single line command. And here, this is the file name of the HDF5 that you prepared according to the format that we discussed before. So once you execute once you run such a command, so what it do is that, so this is the original input you specify to the system. Essentially, it only have some geometric information about your DRM layer. But once you run this command, it will generate the acceleration, the displacement, and the corresponding time vector of your all the plane wave, the 3C plane wave field for each of these DRM nodes. And these motions and the time will be used inside the Real-ESSI program. It will generate a bunch of effective seismic force according to the formulation of the domain reduction method. And with that, you can then move on to do.
Yeah,
Yes,
I'm sorry for interrupting. So essentially, the file that we prepared, the DRM input underscore Kobe HDF5 file, is going to be taken. And this is a database file. And then what the system is going to do is going to add these accelerations and displacements and time. And the only reason, this is a question I had a long time ago, why are they showing in this format? I mean, this is just it's a database, so it doesn't mean that it's ordered this way. It's just that, goes alphabetically, I guess, goes from A to X, A to Z. So essentially, it's just gonna fill up the sections of the database with calculated from the from the solution accelerations and displacements and times, and those are going to be used to create effective forces for the DRM that they're going to be used later on to input motions into finite element model. Yes, go ahead, please.
Yes. Again, so once you do this generation of the DRM motions, it's always good to do some free field verification, because according to the theory of the domain reduction method, so if you input the a DRM motion to a semi free field where you are generating the DRM motion from, it should recover all the free field response. So here we are comparing a FEM wave propagation result from the generated DRM motion, and with the analytical solution comes from that Thomson-Haskell propagator matrix technique. So you can see here we can fully recover the response, and that means we are good, and we can then you can move on to do some nonlinear side response or nonlinear earthquake soil structure interaction analysis.
Yes.
And then just to show you some simulation result. So this is a wave field, a 2D wave field, come from the incident inclined SV wave through a 3-layer system with I think with a frequency 5 Hz and angle of 60 degree. As you can see here, there's some specially varying motion pattern. And so this is because we are specified the wave potential magnet, so this is a harmonic free field response. And we can also, the second case is we are incident a Kobe earthquake records into I think this is a uniform ground with a 15 degree of the inclination. And you can see here, we are comparing this 3C response with like 1D vertical propagation of the response. As you can see here, so when your inclination is about 15 degree, so the horizontal direction, the accelerated response doesn't have much difference, compared with that 1D vertical wave propagation. But if you look at the vertical response, if you only considering the vertical propagation of that 1D records, you won't get any vertical acceleration because all the response is a horizontal excitation, but vertically propagating. But even a 15 degree of the inclination, you can see you can generate about 3 meters per second of this vertical ground motion. And this is what we always observed in the earthquake record, right? Yes. Yes,
so this is actually very interesting. This is what actually Professor Abrahamson, Norm, told me that he heard this from Walt Seal, I think. The 15 degrees sort of default when they assume that waves are not propagating vertically. They're essentially at some, and they always, I mean, depends on the geology, you'll get different angles. But if you use this default that they assume to be non-vertically propagating wave at 15 degrees, you can almost fully recover the horizontal components. It's the same signal. It's a Kobe signal that was recorded on surface. But in fact, the vertical motions get significant because of this interaction, because it's a Rayleigh wave, and this becomes really important. This is a Rayleigh wave. This is not a P wave, because with a P wave you will get quite different response. So this is a very interesting result and very useful for practice. Yes, go ahead, please.
Yes. Yeah. So actually, the vertical acceleration, as Professor mentioned, that we observed in the earthquake records, is not always like the 1D vertical propagating P wave. It actually comes from the surface wave coming from some inclination incident of the body waves. When they have the interference with the surface, it will generate such a surface waves. Yeah, and so it's important that we can model that and use this 3C wave field to do the seismic soil structure interaction analysis. And so here we also provide a bunch of reference that you can look more information to. And again, we're going to give thanks to our collaborators and all these funding resources and the collaboration from these funding agencies. And if you want to know more information, you can always check out our website. There's a bunch of resources there that you can that you might find useful. Yeah.
So thank you very much. So just to summarize, essentially, if you skip your full screen, get out of the screen sharing. So just to summarize, essentially, right now there are two ways of inputting those motions. One is to input some harmonic single frequency signal at any inclination, any wavelength, any frequency, and test the system that way. And the other one is to actually use a real record. You provide the record file. It can be earthquake, can be some wavelets, can also be a sinusoidal, just like what you did before. It can be single frequency sinusoidal, but actually wavelets are good to actually propagate. So there are two ways to actually propagate a single frequency and to propagate any signal. Again, this is more general, but that becomes really, really very useful. Well, thank you very much. We are gonna stop here. We'll continue some recordings in near future. But I'll post these online as soon as I convert them to MP4. Thank you very much. I'll stop the meeting. Let's see here. First of all, I'll stop recording.